Thanks, Kristen.
Great. Thank you, Kristen. Hi, everybody. Yeah, this is Kim Cobb, and I won't speak for David. I'll let him speak for himself in a second, but I kind of approach this space from the observational side. I'm a paleoclimate scientist and observational geek for water isotopes as well, which I've been measuring for over 10 years now in my lab. And I'm really interested in the integration of paleoclimate data and paleoclimate reconstructions of water isotopes into our framework for understanding climate variability and change, kind of at the CLIVAR level. And so that's what brings me into this space. And I think David and I are a good complement to each other because he comes at this from a kind of a different space but overlapping space. So David, I'll let you tell us a little bit about where you're coming from.
Sure, thanks, Kim, and hello, everybody. I think I know a bunch of folks on the call here already. I guess one of the things that I've noticed, I've been working with isotopes in various forms for actually most of my career, which disturbingly is getting up to be measured in multiple decades. That we've done a lot of work with modeling, particularly global scale modeling and also regional scale modeling of isotope ratios in the hydrologic cycle, also the carbon cycle. One of the things that happened over the last 10 years has been a major sea change in the capacity to make observations of water isotopes, including from space-based platforms, in situ deployable instruments, and making collections, particularly from remote sites like island sites and arguably buoys and things like that, aircraft obviously as well. So we're now at this point where there's an emergence of new modeling technology, evolution of existing models really, as well as observational technologies that really pull a coherent set of scientific components together in a way that we can address questions of climate variability with isotopes in ways that haven't been done before. So one of my interests in this group as a whole is really trying to pull that together. There are a variety of folks. As Kim mentioned, my background perhaps is best well characterized in the global modeling domain. There are communities who have been doing this with isotopes for several decades. So too there's paleoclimate folks who have been working with isotope ratios for more than several decades. And more recently, sort of contemporary observations, including remote sensing and aircraft type measurements, that's really bringing together these different pieces in a way that allows us to get at some of these great questions on climate variability and process understanding in ways that are linked to the hydrologic cycle. So for me, that's my little overview of my interest in helping coordinate this activity.
Great. Thanks, David. This is what you see here on the screen is kind of our one-stop shopping that I show at talks and things like that. And so you're all free to steal it as you see fit. Please do. Let people know that this is going on. We're really trying to get the word out. We have a really diverse team of folks depicted here, representing all from people who are concerned about parameterization of convection in our system models, all the way to people who are more exclusively focused on paleoclimate, as well as people who are kind of data repository wizards, people who do airplane campaigns. It's very, very diverse, and we're very pleased to have these folks on board. And I should mention that we have people on board who are not depicted here who stretch into the international domain. I don't have that list handy, but that would include at least Valérie Masson-Delmont, Camille Ricci from France. David, you want to help me fill in some of that if you can remember better?
Yeah, sure. Kei Yoshimura from University of Tokyo as well. Neiji Kurita is involved through University of Nagoya. Did you mention Martin Werner also at AWI? Is another member of the group.
Perfect.
I think that's about it.
Yep. So what we had planned for today was to go over some of our next steps. We had our first telecon, a little bit more of a get-to-know-you kind of telecon amongst our members back in May, and have a bit of a hiatus before we have our next telecon hopefully soon. Thank you, Kristen, for helping to arrange that. And I wanted to share with y'all what we had thought about and hopefully receive some feedback and infusions even at this kind of 0th day, if you will. So I guess, can I toggle forward? I suppose I can. Just to step back, I think the most important goal of the working group is to kind of wade into the space between what has been a fairly niche community, which is the application of water isotopes to climate reconstruction, to study climate processes from the theoretical observational modeling approaches, and then look for those intersections with what we might call mainstream climate science. So looking at those most pressing big picture questions about how our climate functions, how it is changing, and wade right into that space and try to provide some glue there. And I put some potential applications up here. David, you may want to layer up on some of these applications, but these are some very big picture kinds of applications that we see when that become enabled when we do a good job at thinking about approaches and tools and translations into kind of big picture climate questions. So these range from detection attribution of changes in the hydrological patterns. Obviously, the reconstruction aspect is huge, and I feel very untapped with respect to potential here. And I'm talking about ENSO from my own personal domain, but the different modes include decadal variability reconstructions, hydroclimate extremes, et cetera. And then all the way to what David was talking about, which is can we get a better handle on process level mechanisms that might inform simulations in our system models with respect to the global water cycle. That's a very big topic. We're interested in looking at where we can be most impactful from an isotopic perspective. I'm going to pause and let David kind of chime in here.
Yeah, sure. There's a couple of other things I wanted to mention along these lines. One is some work that's really come out in the last couple of years, I think, is this notion of moving some of the paleoclimate records using isotopic traces into a similar paradigm as operational reanalyses and arguably often operational analyses of atmospheric and oceanic state. In particular, we're involved with one of several activities to do a formal data assimilation of paleoclimate data that's within the NOAA family, fits within the 20th century reanalysis, and then the NCAR-NCEP reanalysis in the modern era. The idea here is extending back 1,000 years, and that project's actually just finished up. And the data has been delivered back to NOAA there. The key there is that we can really do reconstructions with paleoclimate data, and to my mind, that represents a real paradigm shift in the way that paleoclimate data overlaps, or paleoclimate science overlaps with more contemporary climate variability type of analyses that are going on from the modern era in terms of those reanalyses. It says something about the strength of the modeling capabilities we have, and also the strength of the data networks that are available to pull those together. And I see the word up there on the screen, so I'll mention it also. ENSO is a great candidate to think of here, that we can now do reliable global scale teleconnection pattern reconstructions linked to things like ENSO from these types of data sets. So it's a real shift and really starting to move towards climate dynamics more so than simple types of in situ or location-based analyses. Extending on that too, that the process, there's a nice linkage between the process understanding and these climate modes. The MJO is one that's I'm particularly fond of. We're doing some work with the MJO, but there are others too. Drought processes in the US is another great example where the hydrologic drivers of drought tightly reflected by the isotope ratios of precipitation, water vapor, and soils as well. And so, I think that's about all I wanted to mention.
Yeah, so I'll layer up again with your permission, David, and noting that the translation between the kind of the past reconstructions of these water isotopes through time, which enable us to infer things about the dynamics that drove climate extremes and variability in the past. And we have these new great modeling frameworks to query those now in a kind of integrated sense. And in terms of what we're missing now is a real thought as to what kind of modern observations of our present day climate system and the water cycle today do we need to ground truth and kind of enable these frameworks to take flight. And so one of the things that the reanalysis framework that David has been a part of, and I've been more tangentially so, is the idea that we don't know very much about the spatial and temporal variability of isotopes today because this has been very much a niche field and has failed to recognize the explosion in technological advances that would enable a much more comprehensive and cheap in decades, kind of robust for decades observational platform. And so I wanted to flag that as one of the goals of our working group explicitly, to think about what will enable the next decades of this research to accelerate these topics listed here. So that's, I guess, what I wanted to layer up there. Yeah, David?
Yeah, that sounds great. Yeah.
Okay, very good. So switching to the next slide then, this is fairly dense, but what are these wonderful isotopes? So we talk a lot about them because they're some of David's and my best friends. But these are oxygen isotopes, in particular the stable water isotopes of 18 and 16, and also hydrogen isotopes in the form of deuterium and hydrogen ratios. And in any parcel of water, the planet-wide, you have different ratios of these two isotopes in the water that you're measuring or looking at or drinking or circulating in your body. And so these ratios are determined by physical processes that we really care about, like evaporation and precipitation, wind and mixing. All of these things are changing the water isotopes in ways that we fairly well understand, actually, which is the good news. The bad news is that we don't yet have quite the observational sets to really unearth these processes as well as we would like. But we know enough about the distributions and variations of these to know how powerful they are. And I'm just noting here on the right-hand set of graphics that, of course, these variations in water isotopes are locked into these precious archives of our climate system of the past. So we have cave samples and coral samples, which are some of the things I do in my lab. Of course, ice cores are probably the most famous application of water isotopes for climate reconstruction, going back, obviously millions of years. And you can extend that to the deep sea as well as into lake sediments and beyond, actually, nowadays. So the number and quality of paleoclimate archives has exploded in the last 10, 20 years or so. And this is the kind of work that seeks to leverage these archives in part of our efforts here. So I'm not going to read the objectives here. They're fairly kind of encompassing what we just talked about. We have mandates on the observational and modeling side, as well as thinking about infrastructure for enabling this science with respect to data archives, which is critically important and currently grossly insufficient to allow the communities that we'd like to reach to really access this kind of data and use it like it could and should be used for climate purposes. So that's another very key goal of the working group. David, do you want to flag anything on here for particular emphasis?
Yeah, I think one of the things that sort of intersect with each of our goals here, which are quite deliberate in their targeting, is this notion that a lot of the accomplishments that have been made using isotopic information relies on really quite elementary theory, that we have a basic understanding of the physics and the chemistry and the biology of what drives isotope ratios. And that stems back, in a lot of cases, several decades, really, basic elements of cloud microphysics and basic biological understanding, things like that. So I've actually achieved quite a lot with sort of elementary, almost first principles types of understanding. The key to this set of objectives here is really trying to move this to the next level, where we know we don't have adequate observations to really constrain the theory that will improve upon what we have. So through the series of objectives, there's a program that's described here that moves from understanding of the basic elements to integration across larger scales, that allows to test, not only test actually, the real key to this is that the existing theory is not being well tested, but it is very successful. So we need to move to a more robust framework where we can both test the theory that we have and understand why it works, but also develop new theory that allows us to further exploit the observations that are slowly but surely coming on. And what I really mean by that is things like the cloud microphysics. The basic controls here are often related to things like diffusion and vapor pressure, saturation vapor pressure, things like this. That's clearly very well understood. What's not well understood is the behavior of the ensemble of these sorts of processes. So, for instance, a coral, the isotopic composition of a coral is related to the saturation of supersaturation of the carbonate as the coral grows, and the isotope ratio is responding to that with a temperature dependence. That's well understood and can be replicated in the laboratory. I think actually it's maybe not as well understood as I'm suggesting here. But the real challenge is how does an ecosystem, a whole population of corals within a region respond to regional climates, the integration between the regional environments versus the localized observations where more information is needed. In a cloud context, that's similar to saying how are convective clouds organized? What are the controls on the organization of convection? Even though we understand how condensation works at a molecular level, and even the dynamics of clouds at sort of fluid flow level, what is the behavior of clouds? So the sequence of objectives here is really starting to exploit some of those uncertainties that bridge the gaps between the microphysical levels that we understand well and the macro scale, which is where we need the information. And the isotope ratios in this plan really sets to bridge that gap in some ways.
Yeah, so just to distill a little bit of what David was just saying, I think at the highest level, what we're looking at are these flavors of water moving around our planet. And one way to think about this is, of course, we're rightfully obsessed with precipitation and its variability and its simulation in models. And one way to think about isotopes in the atmosphere is to recognize that they're integrating through space and time the processes that we most care about. And so if you're frustrated by the patchiness of precipitation, you can use water isotopes to query the fundamental dynamics of a given type of convective system in a way that you couldn't before if you didn't have that tool. And if you're an ocean person and you like salinity, you will love water isotopes because they add a degree of freedom for you in tracking ocean processes like surface fluxes and mixing in a way that you couldn't if you just had salinity. So I'm just kind of illustrating across the atmosphere and ocean boundary some of the high value targets that we have for this working group that even if you really don't want to wade into paleoclimate, if you just want to stay in the modern realm and the future realm, these are the kinds of value added that we hope to deliver, some of what, echoing what David was saying. Okay, so moving on then to the next slide. These are just our next steps that we're going to share with our working group on our next telecon. We have a kind of a nifty package of time before we meet up at AGU this fall, what we're calling phase one, which is to try to get each other up to speed on the kind of the cutting edge of some key topics that we hope to digest as a group and develop task teams around at AGU. And so we'll go into those topics towards the end and definitely collect your feedback if you have some thoughts on additional topics that might be interesting to different panels. We're keen to be as helpful as possible to the U.S. CLIVAR enterprise. So that's phase one. Phase two, going to the next slide, is the next year of task team work. This would include things like the compilation of white papers, perhaps seeded on some of the discussions that we have this fall on these kind of broad scale topics and intersections. We anticipate the creation of a couple manuscripts, probably one review paper on water isotopes in the climate system, as well as maybe some preliminary work that could be crunched forward on the CMIP6 archive as it becomes available. Preliminary talks around a task team focused on data archive designs and stakeholder engagement. And then we do have some exciting outreach products planned, some video, 2 or 3 minute videos that I could see being anchored on the different discussion topics from this fall as well. And so the meetings for next year will be quite significant. We're planning a community workshop, the timing of which is still open, but probably for fall 2019, that would engage a much larger set of the community than is involved in the working group, with representation across the modern and paleoclimate communities as well as the data communities. And then I'm sure we'll have some representatives at the Ocean OBS 2019. I will definitely be at the International Conference of Paleoceanography in Sydney that fall. It's a busy fall. And then we're really gunning towards an AGU town hall in December 2019, where we share with a much, much broader community very much geared towards engaging the modern climate dynamics and modeling community, and really invite the kinds of partnerships and engagements that we hope to really allow to demonstrate the work of our group, its applications, its potential, and hopefully get some feedback as to priorities and ideas for additions as well from the much larger AGU community. This is just for our working group, remembering the deadlines for the AR6 if you want to be included in that. And then moving towards phase 3, obviously trying to wrap up the core body of our working group's contributions in terms of any white papers or manuscripts, thinking about perhaps a special issue. Obviously at that point we'll want to reach out in earnest, hopefully earlier in 2020, to key international organizations that have science plans that we could contribute to, for example, campaigns, observational networks that may be in the planning stages that we would really like to infuse. Some of that engagement will be going on throughout the working group as well as opportunities arise. For example, I am engaged with the T+2020 group on the incorporation of water isotopes to be determined. And the data archive hopefully will be in at least beta form by then, and we'll be thinking about how can we sustain a data archive and under what umbrella. That's all to be determined, as well as our presence at whatever selection of international meetings would make sense. And definitely take your guys' suggestion on things you may know that's coming up that's critically important or strategic for us to keep in mind. And obviously wrapping up, moving into May 2021 there, obviously getting our final deliverables together and having a plan for sustainability of the data archive, as well as identification of some funding sources for any ongoing work that we'd like to achieve. So David, comments on the phases and anything I missed?
No, I think you've done it pretty well. I will just mention one of the key components which comes out of this, and maybe this will actually move into discussion as we go into questions as well, is the notion of the importance of a data synthesis archive. That a lot of what you see here in our phases is targeting these synthesis ideas. There's been a lot of work that's been done by relatively small research groups, individual efforts and institutional efforts as well. But one of the real challenges and one of the reasons why CLIVAR is such an important group for us to be working with is that inherently water is a tricky quantity in that it spans many perhaps disciplinary environments, clearly the ocean, the atmosphere, the land surface being some obvious ones there, also soil hydrology, stream flow and things like that. So the notion of data synthesis here and theoretical synthesis also is really a statement about engaging multiple disciplinary groups. And so part of what you see in the phasing there is bringing together these groups in different ways to look for a whole that's greater than the sum of the parts. And that's certainly true of the data synthesis of things that are existing. It's also true of identifying where the opportunities reside for strategic investments in observational capacities for the long term. And so too, the modeling side of that could be stated as well.
Yes. Okay, so finally to a very ugly schematic on the last slide here. That wasn't necessarily intended for outside eyes, but here we are. So these are some of the topics that we will propose to working group members for their review and refinement as to what are the 4 or 5 main topics that we'd like to collectively digest and share across working group members, so we can infuse each other's work in this integrated space most effectively. We have experts nested in each of these spaces, but the other folks don't know what the other little circles are doing. We want to be very, very clear that this is not a review of all wider isotope research ever, but really passing it through this filter of how can we facilitate rapid advances to pressing climate questions. What are those intersectional spaces that will be the scope and focus of these collections of recent literature advances, opportunities, and for these topical presentations this fall. So David, further comments on this very ugly schematic?
I actually kind of like the schematic. I think it's nice to show them each the different circles. And I think in some ways that these types of diagrams, I always really like that there's sort of several other sort of cross-cutting themes that this sort of type of organizational structure supports. And really the key here, I think back to high school physics, when you learn about the atomic model, and there's I think it was the Bohr model, or predating the Bohr model was the plum pudding model, I guess is how it was described to me in high school. This notion that electrons are sort of blobbed in the middle of atomic nuclei. So I think in some ways that, if I can be quite crude, perhaps, that the isotopic community that's perhaps represented in the diagram that would be like this from several years ago is that it would be a plum pudding model. There's lots of small efforts where there's different sorts of intersections happening at small scales. And what I see in this diagram, the reason I like it, is it's moving from this isolated small entity entrepreneurial type work to a larger coordinated activity where there is the research and scientific infrastructure to support the big problems that we need to be working on.
Thanks for the ringing endorsement, David. I guess that's all we had prepared formally. Really keen to get your questions and feedback captured, and I want to give a special shout out to Sam Stevenson, who's part of a working group, who I see on the call. So hi, Sam, and thank you. Kristen, you want to take it back?